So I hope you can see my slide. I hope you can see my slides now.
Yeah, looks great.
It's a pleasure for me to be here at this meeting. I'll come back to that on the next slide here. So I will tell you about what nanoscience and surface science can be done at the European XFEL. So put here, it's all about the timescale, and I was very happy listening to the talk by Elias, where he talked about the residence time of water on the surfaces of, I think it was nanoseconds, and that's a very interesting timescale for us. So we are a facility like ESRF or ILL, so an international facility based in Hamburg. We have been operating since September 2017. You can see a picture here of our inauguration, and here's a picture of the overview of European XFEL, and I'm standing here in the back with the glasses. So what I wanted to show is this here, where we have seen this so many times. It's faster than Moore's law, but maybe more like this picture here, because listening to the talks, it's lovely to see the crystal truncation run and reflectivity curves again. I'm now basically doing talks and having a suit on and a tie, etc., as you see up on the right. But you see, this is roughly when I started in '81 doing surface diffraction, and this is how I looked when I did the crystal truncation rods. I'm pretty sure. So it's a pleasure of listening to all these talks, and it's a pity that we cannot meet. There are a couple of old friends in the audience, not too many, which is good, because that means that the audience is young and there's a lot of new people and staff coming in. So it's a pleasure for me to giving this talk. I will tell a little bit about what European XFEL is, how does it work, and then give some examples of what nano and surface science can be done. I cannot give these nice presentations and with detailed analysis because I'm too far away from that, and that that's our users which should do that. But I can give you sort of where are we and encourage you to start to think about what kind of experiments could eventually be done at European XFEL. XFEL has already been mentioned a couple of times during the presentations. So as I said, it's about the timescale, and you've probably seen this picture here, where you sort of see what's the human timescale. And if you take this horse running here, you want to locate the horse or within about a centimeter, it has a certain speed. That means that the human time scale is milliseconds, and then that compares then to the time scale we know from solid state physics. So I taken this acoustic vibration from the lectures I gave when I gave lectures at the university, and if you sort of calculate what's the time scale, then you come into that's tens of femtoseconds is the time scale that atoms move on. And if you want to catch pictures of atoms that needs then you need to have pulses which are of femtosecond length, and that's exactly what we deliver. So European XFEL is and LCLS and other free electron lasers are there to study dynamics. So just for the audience here, what's the difference between a synchrotron? You've seen the several talks already with the synchrotron radiation data, and that's simply the pulse structure. We have max 4 there on the left, and it will give pulses, roughly of this order of magnitude, 10 to the 9 photons per second, which each have a duration of 100 picoseconds, and they come with a certain frequency, 10 to the 6 photons per second, whereas a free electron laser provides you fewer pulses. At least European XFEL, we have up to 27,000 pulses a second, but the pulse duration is much shorter. So you can see the pulse duration is only some femtosecond. I believe we are delivering pulses, from a few femtoseconds up to maybe 100 femtoseconds, and they contain a lot of photons compared to what you have with an undulator, and that has certain consequences, namely that free electron lasers provide exceptionally strong beams. And just to underline this message, I have taken here a picture where we have a piece of steel, where you shoot the focused X-ray beam onto your piece of steel, and then you drill a hole in the steel in less than half a minute. So it tells you that if you focus the very powerful beam, you have a destructive beam, and that of course has some consequences, but also some features that you have to exploit when you do your experiment. So many of you have probably seen this here, that the focused X-ray beam is very intense. So here's a picture from a publication about 20 years old, where you have a protein being put into the beam, in the focused X-ray beam, and then you can see that within a few, some tens of femtoseconds, then the sample is destroyed and evaporated. And the trick is that you need to take data, you need to take a image or a scattering data before the sample is destroyed, and that is something that has been proven to work. But it means that you don't have, if you focus the beam, and I stress, if you focus the beam, there's not too much time to actually take the data on a given sample. So the overall principle here is that this is slightly different from a synchrotron. You have a LINAC where you accelerate the electrons up to, in our case, between 14 to 17 GeV. And then you put them through a long undulator, and then you dump the electrons in a dump, and then you use the X-rays that are then coming out. So you only use the electrons once or maybe twice if you have more than one undulator in a row, but it's not circulating, and that's one of the major differences to the synchrotron. Now here's a general layout of our facility. We are placed in Hamburg near Daisy. You can see Daisy here on the right. You can sort of see parts of the Petra ring, and we have the electron injector on the Daisy Barnfeld campus. And then we have a 3.5 kilometer long tunnel, which is typically 20 meters below ground, depends on where you are. And it's a superconducting accelerator, 2 kilometers long, where the electrons can be accelerated up to 17.5 GeV. And you see on the picture up there with the yellow modules, that's a part of the superconducting undulator. And then we have to the left here, we leave the state of Hamburg, go into the state of Schleswig-Holstein, where it says Schenefeld here, that's where our headquarters are placed, and that also where all the experiments are taking place. At Ostrava-Born, we then we can then put the electrons into two different directions. Here are some of the undulators and photon tunnels. This is the undulators in this case here, because we need to have enough undulator length to do this, what we call self-amplified spontaneous emission, the Sartre principle. I will not go into that today, but that requires undulators of about 150 meter length. So it's a really a big piece of equipment, but it really works astonishingly well. I mean, LCLS, they're not superconducting, but LCLS has been running for more than 10 years, and we have been running now for 5 years, and the accelerator runs really, really well. And here's then the experimental hall in Schenefeld, where the experiments are being conducted. And I show you here a sort of the experimental hall. So I would go through little bit from some of the possibilities of the instruments. So we actually, I now see this. It says here typically we're running in 12-hour mode, so we can deliver photons from at 3 different instruments basically at the same time, because the electrons we produce can be guided through one of the 3 ondulators we have here. We call them SARS-1, SARS-2, and SARS-3. That's where the electrons can go through. So for instance, here the electrons would go through SARS-2, then they will provide beam to one of these 2 instruments up here, and then the electrons will be put into XTD3, and then there's a beam dump over here. And then we run that, for instance, we can take the example of SARS-2. It could either be 12 hours experiments on HED and then 12 hours on MID. So they shift twice a day, or at the moment we run that there's 1 week for HED and 1 week on MID. So we have 6 instruments here. I will give some examples of the science that is being done on these 6 instrument science that hopefully is of interest, and would also could inspire you to think about what kind of experiments could eventually be done at XFEL. We're studying dynamics of surfaces, interfaces, nanosystems that cannot be done on a conventional facility. We are that you see there's no, if you look through the instrument description, there's no specific surface science instrument. So that's something we will come back to. But there is a 3rd port in progress, which will be in operation hopefully end of the year, where open port where users can come in with their own equipment, and for instance it could be a place where one could do photo emission and stuff. SARS-3 is for soft X-rays, so that's only for the softer X-rays, but some surface science could eventually be done there, spectroscopy, catalysis, and things like that. So the key parameters of the facility, and that's depending on that we have a superconducting accelerator that gives a lot of advantages. So we have a particular running mode where we have what we call the burst mode, that pulses are coming in bursts or trains 10 times a second. And within this train, we can have up to 2,700 pulses. Each of these pulses are spaced by 220 nanoseconds if we run the highest possible rep rate. And that can be changed very differently from a synchrotron experiment, is that the users are very much involved in defining the parameters, because typically the beam delivery is designed per instrument, number of pulses, photon energy, of course, has to be defined all over, because that depends by the electronegativity. But there's a lot of discussions between the user group and the accelerator and instrument groups. We can the photon deliveries up to 25 kV. Actually, we had lasing up to 30 kV. So we actually can go higher, and then I mentioned the pulses and the pulse duration. But this one of the key parameters of European XFEL is a high rep rate, where you can collect a lot of data, because it means that you have collect, for instance, scattering images 2,700 times in each, or up to in each train, and that means you have to collect maybe 3 or 4 or 5,000 scattering images per second. So, and this here is a very important slide, that experiments are typically done in a radical different manner than at a synchrotron. So I got this slide here from Peter Fromme from Arizona, and I think it illustrates quite well how many, not all, but how many experiments are actually done. So here you have a jet. You have a jet which sprays in crystals into the beam. So I think I have a slide which shows this later on. And then you have, with this yellow here, you have these trains of pulses coming in, and then you hit one of these, or you might hit a crystal, and then you collect a scattering images over here. Now I have to say the hit rate is could be 10%. That means that only 10% of the pulses actually would hit a crystal, or it could even be below 1%. So it depends a little bit on your sample injection system. The second take-home message is here. I already indicated that within the focus beam, when you hit a crystal, the crystal is gone, it's exploded, it's destroyed. And this is very, very different from what I did when I did surface science measurement. And what you do is that you spend, you're really careful about your sample. You spend days and weeks preparing it, growing it, and then you're very careful not destroying it when you do the experiment. And then you study maybe this one sample for a week. Now here is completely different, that the samples are put into the beam, and you only get one shot on every sample, on every crystal, and then you have to collect enough information that you can get that you can analyze the data from your crystals. So here's a jet, which is one of the first experiments we have done. It's a protein diffraction experiment, but just to show, this is the jet showing into the beam, and these interruptions is when the beam, the X-ray beam is hitting the jet, then it interrupts the jet, and you see this disruptions. The art of sample delivery is very tricky, and for instance, I wrote here 100 meters per second. That's the speed of the jet. If you don't get the right speed, things will, it might not actually work. So there's a lot of art and wisdom in how to do that. But we have a group, a sample delivery group that are experts in these jets. So some of the first experiment here is maybe not nanoscience, but it was time resolved. So the idea is to look at changes. So this here was a protein crystallography data where you could look here. This was a combined data set from LCLS and European XFEL at a synchrotron, where you could see structural changes on the, here in this case, on the picosecond time scale, where some of these data here was taken at European XFEL. So this is the kind of time-dependent experiments that we would really like to do. And this was done, as I said, in this way of collecting data, focused X-ray beam samples being jetted in, and then you collect many data. So the complexity of experiments is actually pretty high, and therefore it's one has to involve with European XFEL, with our staff, in order to do this experiment. I mean, the photon delivery is actually works extremely well. There's optics, there's diagnostics. Sometimes you want to do pump your sample with an optical laser that then also have to work. I already mentioned the sample delivery. We have the detectors, which takes a lot of data. We have big detectors, and then you end up with a lot of data analysis at the very end. And you give you this here example. So this here is a measurement of a crystal truncation rod in the 80s. It's done much more. I saw all the nice crystal truncation rods presented earlier today. It's of course completely automized. It's not like we did it in old days here, that data was stored on paper, etc. But just to underline this here, that these days are completely gone. We collected in the last run of 21 the facility. We ran 3 experiments at the same time. 2 of them actually produced together more than 6 petabytes of raw data. So it really tells you there's a lot of data analysis that you need to take care of after you've done your experiment. But you know, if you align and collaborate with our staff and with other user groups, it's something that you can actually do. So so here here's the setup again with the 6 instruments, and we have here the description of the 6 instruments. I would not go in detail explaining, but I'll give you a few examples of what could be of interest for you. Here's the FXE instruments, just to show you how it works. There's a lot of optics at the beginning. You have the sample sitting here. You have the detector on this robot arm for doing spectroscopy, and then you have a big detector at the very end, collecting, scattering images, and you can see a nice picture of this detector here. And it collects, can collect up to 5,000 frames a second, roughly. And typically what they have been doing here is looking at spectroscopy. This is an enzyme experiment where they looked at the time difference between exciting the experiment, looking at differences in the excitation, in the emission spectra, and they can then follow that on time scales, you know, up to down to a few hundred femtoseconds, and that actually work quite well. Now here's another experiment which is actually published. It's from the group in Göttingen, Tim Sallet, and it's to some extent actually a surface or interface experiment, but it shows you the capabilities of what you can do at these free electron lasers quite well, because it's a question about nucleation. So it's with a strong optical laser, you make water bubbles in the water, and then you look how does these water bubbles actually form, and what's the time dependence of when they are actually forming. And you can see at the bottom here, it was published about half a year ago. You can see here, here it's nanoseconds. The duration of the laser is in a nanosecond regime, and then you can see how the water bubble is expanding, and that's showed here on the next slide, where you can see that of course when you hit the water, the bubble starts, and then it's empty in the middle, and then you see these images here are scanning images that are converted. They are with holographic techniques. So these are the real images here. Here we have the X-ray holograms, and then you can measure the density of the rim here. That you actually have a density that is higher at out here at the rim when the water bubble expands, and that's about I think it was 20 to 30% higher density, and you can see that the interfaces are actually very sharp. And now this here shows one particular water bubble, but doing these experiments with collecting data, you collect data for many different water bubbles. So you can actually do the statistics also afterwards, and you can look at all the ones that are different from the average one. I think that's is an important message. Here's a similar kind of message. This is from Optica, also a user publication from last year, where you spray in not proteins but gold nano, in this case nanoparticles, and then you afterwards look at the many different nanoparticles you have scattered from, and then you can do the statistics afterwards. And in this case, you have 10 million nanocrystals you have actually hit. Then you can, because you have collected a lot of you have a lot of statistics, so you can then classify what kind of nanoparticles you actually hit. how big they were and what shape they had. And that means that you can, in a statistical way, go in and analyze the experiments or the samples you actually had. And here's some examples that they actually got out. There's also you have a big magnetic program at science program at European XFEL. Here's one example on the SCS instruments on ferromagnetic multilayers, where you look at the nucleation and coalescence. This was a user group from ITMO in St. Petersburg, where you look at small angle scattering pictures versus delay time, so you can study the dynamics. And I think this is something that could be emphasized, in particular that the magnetism is actually a very big part of our scientific program. We also look at core shell nanoparticles. This is now done here at the SQS beamline to look at the core shell and see, what's the core, what's the shell, tune in the resonances. And this data has not been published yet, but I think nanoparticles will be one of the topics that will grow here in the next couple of years. We also did some surface science catalysis here. I cannot show results. I can just show that they have actually been here doing some very nice measurements. I think Edwin is in the audience somewhere. So look at how these nanoparticles might change shape after they hit by a short, powerful laser. You see here a picture of the complicated setup, and there's some preliminary data analysis going on, which I'm looking forward to hear more about. The experiments were actually quite recent. The last example, I look at the watch, a few minutes left. The last example is actually reflectivity, and I was quite excited to see when they did this kind of reflectivity measurement. So they look at gold films, and then you take the reflectivity with the gold film. You do GSAX basically, then you hit this gold film with a very powerful laser, and then see what actually happens when you heat it up. Basically make a plasma. Can you follow the transition of this flat gold film when you heat it up and then it actually evaporates? So it tells you you don't have too many shots on your sample here before it's actually destroyed. But I think it's some very interesting dynamic experiments that could be done here. So with that, I would like to end and say, I already said the experiments take, typically we allocate 5 days or 60 hours based on excellence proposal system, exactly as you are used to from other facilities. We hope to at some point to get up to about 170 experiments a year. We are not there yet, but we are something like a little bit more than actually halfway. And I would say with the conclusion, it's plenty of opportunities for interface science. I think you should contact us, and I would be really thrilled if we can do a lot of good science and interface experiments. I have some, when I wrote scientific reports 20 years ago, but you can use European XFEL for friction and sliding and things like that. Would really be interesting to do something like that. And you can join our users meeting, which will take place in about 2 weeks from now. So with that, I say thank you for your attention.
Robert, thank you for a beautiful overview of an amazing